So refraction is really the bending of light. We've all seen this when we try to catch a fish in a pond, and it's not where we think it is, or sometimes you can see a straw in a glass that looks like it's bent funny. It turns out that light travels at different speeds in different materials. So it travels at different speed in water than it does in air. Air is very much the same speed as it travels in a vacuum, 3 times 10 to the 8th meters per second. Because the air molecules are so far apart, as far as light is concerned, it seems like a vacuum. But it travels at a different speed in water and glass and gasoline and benzene and any clear material, acrylic, any material that's clear, light travels at a different speed. And you can sort of see why that might be true, because materials are made of atoms and light is electric and magnetic fields, and they interact very strongly with the electrons and other charges in the atom. And so that causes it to either slow down or to a different extent in different materials. So the index of refraction So the index of refraction is the ratio n equals c over v. So n is called the index of refraction. C is the speed of light in a vacuum. V is the speed of light in a material. And so since the c, the speed of light in a vacuum, 3 times 10 to the 8th meters per second, is the same all the time, this number changes because the speed in the material is different. Water has has an index of refraction of 1.33. That means that the ratio of the speed of light in a vacuum to water is 1.33, or about 4 to 3. And so instead of being 3 times 10 to the 8th meters per second, the speed of light in water is about 2.25 times 10 to the 8th meters per second. A typical number for glass, glass has a wide range of numbers, but a typical number for glass is about 1.5, something like that. Diamond is around 2. It turns out the higher your index of refraction, the more bending you get. And I'll talk about that in a second. So let's look at a beam of light. Let's look at this red light ray hitting a boundary between air and glass, say, or air and water, it doesn't matter. So what I want you to imagine these black lines to represent is the peaks. Light looks like this, right? Some kind of wave. So we'll be looking at the electromagnetic waves. We'll be looking at the oscillating electric field. So what I've done is the light is, as it's going this way, it's waving up and down. Each one of these lines is the peak, and here's the next peak, and here's the next peak, and here's the next peak, and so light's moving this way, and it's entering this new material. And so what I want you to recognize is that as it enters this new material, it slows down. And so you can kind of see, since it's coming in at an angle, that the beam that's over here, this is technically not an infinitely thin beam. This is a flashlight beam or something like that, right? And so the peaks that are over here are going to hit the glass before the peaks that are over here along the same row. And in fact, this edge hits it before any part, and so this edge gets more time in the glass than the rest of the line does. And so what this looks like is that, because this guy got in first, he only got to travel a tiny distance. This guy was barely in at all, and so he only slowed down a little bit, and you get this kind of effect. And so the next row of this looks like this. right? This row would be here, and this row would be, as it came up, would be here, and so on. Had they kept going straight, this row would look like, we would get these rows that look like this, but instead what's happening is that because this side is getting into the glass first, it's getting slowed down, the other side's sort of catching up to it, and so now you can kind of see the direction of the light is now this way. And so the light is bent as it comes into the liquid. And this is really, you can think of this thing, by the way, as rows of soldiers marching from, pavement into mud. It's the same thing. These guys on this end get into the mud first, and so they're slowed way down. And for a given row, the ones who are out aren't slowed down at all. The ones who are in just for a little bit are slowed down least. And so you get just a bending of the rows. By the way, this is the same reason that when you're driving your car off the road, you're driving your car down the road and one of your front tires catches some dirt, your car pulls to the right as you catch the dirt on your right side, because that tire slows down and it causes your car to turn, just like this is turning. And so what people usually do is overcorrect and then run off the road on the other side. And that's a challenge. But this is the effect that's called refraction. And it's the bending of light that's the result of the fact that the light travels at different speeds in these two materials. I might call this N air is equal to 1, because the speed of light in air is the same thing as the speed of light in a vacuum, basically. It's still 3 times 10 to the 8th. And this is N glass equals 1.5 or something like that. So if we were to draw this out, I didn't leave a lot of room here, but let me just see if I can draw this. So we would call this theta incident, and this theta refracted. Usually it would be 1s and 2s, so this might be theta 1 and this might be theta 2. But that's what refraction is. When you're going from a low index of refraction to a high index of refraction, the light bends toward the perpendicular. We already talked about the principle of reversibility. If I reverse this light, if it went from a high index of refraction like glass into a lower index of refraction like air, you would say the exact opposite thing. So you could look at these rays going in the other direction and say, hey, this end got into the high-speed stuff first, and so it jumped ahead like all of these guys did, and so on, and so the light would bend the other way. We could amplify this a little bit, or talk about it a little more as light going straight in. Imagine instead of being at an angle, the light goes straight in, right? In that case, there's no place for it to bend. What the rays do, every part of the peak gets there at the same time. So I would see this and this and this, and maybe one right along there. But then as I got in here, they would be scrunched together because they're all traveling in a material that only allows light to travel at a slower speed. And so I might call this, lambda 0, and this would be lambda 1, or something like that. Right. The index of refraction, so in our example where it's air and glass, it would be N air times lambda air, which would be this guy, equals N glass times lambda glass. For since the index of refraction for air is just 1, because it's the speed of light divided by the speed of light, and so we could just say lambda air is equal to N glass, or the wavelength in glass, Or we could say the wavelength in glass is equal to the wavelength in air over the index of refraction of glass. And so that would be, since that's 1.5, if you knew the wavelength in air, you could know that the wavelength in glass is that divided by the index of refraction of the glass. A couple other things to note about this. The frequency is just the rate at which waves are going by you, and you might think that the frequency changes, but it doesn't. The rate at which these guys are hitting the surface is constant, and the rate at which they're going through the surface is the same. Otherwise, they would be piling up somewhere. And so it's the same thing if there's a row of soldiers going by you once every 10 seconds, then that's happening out here and it's happening in here. They can't be disappearing. And so they're just much closer together going by you once every 10 seconds than they are out here. And so we would say F0 is equal to F1, or the frequency in the air equals the frequency in the glass. So here's the problem with this, looking at the wavelength difference between air and the vitreous humor, which is the fluid in your eye. The wavelength range of visible light is from 400 nanometers to 750 nanometers in air. What is it in your vitreous humor, which has an index of refraction of 1.34? If you remember, the wavelength times, the index of refraction times the wavelength is constant. And so NV, the wavelength in the vitreous humor, is N air times the wavelength in air over the index of refraction in the vitreous humor. And since this one is just 1, since the index of refraction of air, then the wavelength in air over the index of refraction of the vitreous humor is equal to the wavelength in the vitreous humor. And so if I do so lambda v, if I do the 400 nanometers, that gives me 298 nanometers, or the wavelength in the vitreous humor for a 750 nanometer is